Welcome to Spring LIB.
This is the answer to Chapter 31, problem number 60 from the Smith Organic Chemistry textbook. And this problem talks about melmac, which is a polymer. We're told that it's formed from melamine and formaldehyde. And we're asked to draw a stepwise mechanism for that synthesis. So, since we have an amine and formaldehyde, hopefully everybody should be aware by now that the first step here is definitely going to be the amine attacking the carbon of the formaldehyde. It's a carbonyl carbon. It's susceptible to nucleophilic attack. So that's going to look like that. So the product of that first step will then be this. Apologize. For some reason, I struggle a lot to draw these six-membered rings with three nitrogens in them. Okay, so there will be a new carbon-nitrogen bond there. And so this nitrogen is now going to have four bonds. So it will have a plus charge on it. The oxygen has an extra lone pair, so it's going to have a negative charge on it. And in order to relieve those charges, a proton transfer is going to take place. So we can draw that as a lone pair of the oxygen taking this hydrogen. The electrons, that's not good. The electrons of this nitrogen-hydrogen bond reverting to the nitrogen. So that's going to relieve both of these charges. So that's just a proton transfer. And so the product after that step is going to be pretty much exactly the same, but with those charges resolved. Right. Okay. So there's that product. So this problem does not say that we're using acid anywhere. Acid's never mentioned. But in order to make this mechanism make sense, we need to invoke some acid. So we'll use the stereotypical HA for acid. So there's our HA. So the next thing that's going to happen is a lone pair on the oxygen is going to grab the acidic proton. And so that takes us to here. So we now, where we had an alcohol in the previous step, we now have an H2O plus. There's a positive charge on that oxygen. And of course, this is now a good leaving group. So OH can't leave, H2O really wants to leave. So this carbon-oxygen bond will break and the water will leave. At the same time, the lone pair on this nitrogen can add in there and form a double bond with that carbon. So rather than forming a carbocation at the carbon that the oxygen just left from, instead, this way we're putting the positive charge on the nitrogen. And you should remember that makes sense because we always want to put charges on more electronegative atoms. And so nitrogen is much more electronegative than carbon. And so that makes sense. So now we have our nitrogen. It's got one hydrogen on it. It's got this double bond to carbon. And so since nitrogen has 4 bonds here, it will have a positive charge. So now what can happen here is another molecule, a second molecule of melamine can come in. Give me a moment to draw that. So here's our second melamine. Oh man, and I apologize. It looks like I omitted an amine group in almost every single one of these drawings. So melamine has 3 of these amines on it. So I do apologize. There we go. At least I caught it now. Right. So there we go. So this second molecule of melamine can now do a nucleophilic attack on this carbon. These electrons will kick over to that nitrogen, relieving that charge. And that reaction, the product of that reaction, is going to be 2 melamine molecules bridged by a single carbon. So that's going to look like this. Okay. And so, of course, this nitrogen that just acted as the nucleophile now has 4 bonds. So it's also going to have a positive charge. And so, lastly, the last thing to consider here is just relieving that charge. So we can use the conjugate base of the acid that we invoked earlier. So we can say we made some A minus, some conjugate base. So we can call on that. And that's a negative charge. We can call on that to come along with its lone pair and grab one of these hydrogens. Those electrons will revert to the nitrogen. And now we have our intermediate here. And so we have two melamine molecules that have been linked by this single carbon bridge from the formaldehyde. Let me just finish drawing this. And so I believe that's all that this problem was asking for. Just double check. Right. Yeah. So it's just asking for the mechanism of that part. So to get so that what I've drawn here is the answer. This is the mechanism for that condensation, and then obviously to get to the final product, the actual melmac, where it's a network of these melamines linked by single carbon bridges. All you would have to do is consider that every available amine here could undergo the exact same reaction with other formaldehydes, and so they end up all linked together in a pretty sturdy network. And so that's the answer to chapter 31, problem number 60.